Hey everyone, welcome to our session here. We're going to review quickly acids and bases, mainly for the ACS exam. And I'm here at Smith College in Northampton, Massachusetts. This is my dorm room, and I'm here for a guitar workshop. But I want to run through these with you guys real quickly. So let's say that there are several factors that you want to consider, and I've written those out here. And I also want to show you about some general Pka values, which I find helpful, especially when you're comparing multiple functional groups. So first, let's start with a question like H2O versus H2S. Which one is the stronger acid? When I'm looking at atoms and that are different periods of the periodic table, we're going to say size is the main issue when you have different periods. And based on size, as you get larger, conjugate bases, so here are the conjugate bases, as they get larger, they're able to stabilize that negative charge as it spreads out more. So when you get a larger conjugate base, the charge is more stabilized. So you're going to have a weaker base. So O2 minus is a stronger base than S2 minus. And then when that happens, then their conjugate acids are going to be the opposite. So as I get O2 minus is stronger than S2 minus as a base, H2O is going to be weaker than H2S as an acid. So I'm going to have a stronger acid. And then if you just want to memorize something, you could just say the larger this is, the stronger that makes this as an acid. But the reason behind it is that their conjugate bases are stabilized by larger sizes. More polarizability, if you remember that term. The ability to spread out electron charge. Okay, the next factor I want to talk to you about is what happens when you're in the same period, but you want to go across a period. So let's say nitrogen versus oxygen is the only difference between those two, really. So if you're going across the period, size is no longer the dominant factor, and their difference is mainly attributed to electronegativity. So as you increase electronegativity from nitrogen to oxygen as you go toward fluorine, your electronegativity of the atom is increasing. Again, looking at their conjugate bases, you have NH2 minus or OH minus. And we know that oxygen, being more electronegative, prefers to hold on to negative charge better. It's because it has a greater effective nuclear charge, more protons. And so given that this is more stable by its charge, even though you're programmed to thinking OH minus is a strong base, when you're comparing it to NH2 minus, that's the strong base, stronger base, right? So as we increase the electronegativity of the atom that's different between these two, N versus O, then we have a weaker base because this is more stable by the negative charge. Then going this way, then the opposite is true. We're going to have stronger acid as we go across. And you guys probably know that because NH3 is more of a base than it is an acid, right? So water is sort of a weak acid, weak base, and this is sort of more of a weak base. So another factor is charge. If you look at H3O plus versus H2O, sort of a no-brainer. You think of that as a strong acid, right? And this is a weak acid. But why is that? A lot of that is because this will have a driving force behind it of wanting to neutralize. And so this wants to do that, whereas this being neutralized or being an acid would result in this, and this is actually stronger than that is. So we're fighting against stability here, right? We're going from something less stable to more stable, and that doesn't make sense. So just based on charges and wanting to go toward neutrality, that can also be an indicator of acid strength as well. Now let's put some of those concepts together, and I've got a question for you. My question is rank these in order of acid strength, so from weakest acid to strongest acid. So along these lines, we just learned about charge, right? So we know these two are definitely stronger than those two, and going through sort of some of the ideas behind electronegativity, we learned that H2O is a stronger acid than NH3, due to electronegativity. So after that, though, then we have NH4 plus versus H3O plus. And so you know H3O plus goes to H2O when it's acting as an acid, and ammonium turns into ammonia. So electronegativity-wise, nitrogen is less electronegative, so it's more able to share its lone pair than oxygen is. Oxygen's sort of greedy. It wants to keep its lone pairs for itself. And then another reason why is oxygen wants to be negatively charged, not positively charged. So nitrogen's better at becoming a positive charge than oxygen is. So there's a lot of different ways you can look at that. So because NH3 is a stronger base, that means NH4 plus, its conjugate, is a weaker acid than H3O+. Another way is later we're going to talk about pKa values, and something that I always remember is hydronium is close to pKa of 0, whereas ammonium is a pKa of about 9 to 10. So that really helps as well. And H2O is a pKa of about 15.7 and or 16-ish is, easier to remember. And ammonia is a pKa of 35. So you can also tell from just a general knowledge of pKa values as well. It could be a really nice shortcut if you're willing to memorize a few of those. The next factor is induction, and I commonly see that with carboxylic acids. They'll put some halogens here. So for example, a Br here versus a Br here versus no Br. So you guys know that carboxylic acids are acidic, but putting a halogen on them affects the charge distribution. Once this becomes deprotonated, and that charge can spread out then, once that's negatively charged, you can have it spread out more versus spread out less. Okay, so here, once this becomes negatively charged when I deprotonate, so it's a matter of how much that negative charge is concentrated in that area. Here, I have no bromine to pull some of that charge away. So this is going to be the most concentrated charge. Here, this bromine has an effect of pulling some of the charge, but this bromine is closer to this area, so it's going to have a stronger effect due to proximity. So this will be spread out more. This will be a little bit less spread out because the bromine's farther away. And this will be the spread out the most. This bromine has a better effect on withdrawing the electrons through the carbon chain. And that's what I call induction, is that longer range pulling or distribution of the electrons. So based on induction, I would say probably this was my this is my strongest base. That means it's the least stabilized by induction. So the acid, its conjugate acid, is going to be the weakest. Whereas this one has a greater inductive force because of proximity. The bromine can have a greater effect when it's closer to the protonation site. So its conjugate is going to be the strongest. So here I would expect this acid to be stronger. And this one will be in the middle. It'll be better than this, but not quite as good as this because the bromine's farther away, so it doesn't have quite as much of a pull or inductive force as this one does. And my shading here is to show you concentration of charge. Most concentrated, second, and least concentrated. So here's my last example, is this acid versus this acid, where this is the hydrogen that comes off. And you guys can probably tell that I have some resonance going on here. So once this becomes negatively charged when the H disappears, I've got resonance here, resonance delocalization here, which stabilizes that, but I have more here, right, as I go there, and I can also go there. So the charge is much more spread out. Here it's sort of localized here, somewhat delocalized, but here is even more delocalization. So this is going to be a tad bit more concentrated here than this is. So this is more stable due to more resonance structures that result, or more delocalization of the charge. And so this is going to be a weaker base or stronger acid. Its conjugate is going to be stronger. An application of that you see sometimes is looking at the acidity of different phenolic groups, or phenols. So I'm going to draw two phenols for you. And we're going to try to figure out which acid is the most strong, or which of these phenols has a lower pKa. That also means which one is a stronger acid. So stronger acid. So let me have you think about that and think about resonance due to the conjugate base. So again, we're going to look at the conjugate base of these, and we're going to look at how resonance might influence the strength of the conjugate base. So here's the conjugate base of phenol with the H gone, and you can see there's delocalization throughout, even through to the nitro group. This is often abbreviated NO2 down here. Okay, so it's good to expand it out because you can see the resonance delocalization there. Here I could take the lone pair, and I can go here, but at this point I have to do that. So negative charge is going to end up only around the ring, not through the nitro group. So because of this resonance, this is more stable as a base, or or it's a weaker base. So that means its conjugate is stronger. So notice the para versus meta versus ortho, which I didn't draw ortho, but you could go through that example as well. And you'll see that ortho-para, in this case, has the ability to delocalize into the side group, whereas this one doesn't. Then I forgot one more thing, which is hybridization. And you guys may remember that the pKa here is different from the pKa of a double bonded H, and that's because their hybridizations are different. So they're attached to carbons with a different hybridization, sp versus sp2, right? So sp versus this is sp2. With hybridization, it depends on S character. You know that sp has 50% S character. That means that when this is deprotonated, those electrons sit closer to the nucleus because of greater S character. So that means this lone pair is more stable. So this is a weaker base. Okay, whereas sp2 and sp3, those electrons sit farther out because of greater P character. So here, because that's a weaker base, since those electrons are held more closely, it's sort of like the same thing as electronegativity. It's almost like this is more electronegative than that is. So with that same concept, this is a weaker base, that means this is going to be my stronger acid. So speaking of which, there are certain functional groups, so just by looking at it, you can tell who's stronger than who. And here's a table of pKa values that could be helpful. So I built this chart from strongest to weakest. So I got strong acids with a pKa of about 0. I just think it's useful to know. Hydronium you can think of as pKa of 0, or HCl, HBr, HI, my strong acids. These are really helpful. If you can remember, HF is not as strong because F is so small or very electronegative. You can think of it as, I think of it as smaller than the others, which makes it much less strong as an acid. Another one that's useful is pKa of 5. That's going to be my carboxylic acids. So this kind of chart really helps you determine between multiple acid groups, like if their structures are really different, then it's harder and harder to compare, you know, how does the effect of a carbonyl, what effect does that have versus a halogen, right? It's sort of apples and oranges, so it helps a little bit to have some general ideas of that. So with the phenol and with my protonated amines or ammonium type, you know, nitrogen with a positive charge, you know, or an R group with, you know, something like this. Okay, basically those guys have a pK of about 10. And then about 15 or 16 are my alcohols. So these H's here, or water, right? This H there, same kind of thing. I also have at 20 about 20 we have our carbonyl hydrogens, so the alpha hydrogens of a carbonyl group. That's what we've been learning about in OChem 3. And of course, if you have two carbonyl groups and you have alpha hydrogens in between, those are going to be more acidic or lower pKa than 20, so somewhere in between these. That's already a lot to remember right there. That could help you a lot. If you can, try to go a little further and say that at 25 you've got your alkynyl hydrogens, and at 35 you have ammonia and or, you know, amines, NH2. These guys don't really like coming off very much. And then around 40 you have your alkenes, and at 45 to 50 you have your alkanes, which really aren't good acids. So if you can remember these, that's helpful too, but these are very common. I would learn those. And that's really useful for a problem that you might see on the ACS where you have a molecule with multiple types. You know, you've got this kind of thing. And so when you're looking at something like that, you know, it's really hard to compare. You know, how acidic is this versus that? Because there's multiple factors. There's resonance. The atoms are different. The charge is different. How do you know how that all plays out, right? So that's where this chart can come in handy. So looking at the phenol, I know these are my acidic groups, and just knowing some basic pKa values, I can pretty much reason it out, okay? And maybe here it would be a little bit of a toss-up, but you know, they might not put both of those on there, but they might do something that's a little bit more different. Let me make it a little bit more clear. Maybe instead of an amino group, I can use an alcohol here. So it's just a regular alcohol with a pK of about 16, see? So you can play around with those things, and then you can see, oh yeah, this is the strongest acidic, most acidic portion, then this one, then that one. All right, good luck with that.